All right, wonderful. Well, one of the things I always like to look at is do we have at least 100 people here? And we have more than 100 people here already. So I'm very excited to talk to you all today about Postgres 18, which was released this morning, or evening, depending on where you're at on the globe. So thank you everybody for making a time today. My name is Lucas. I'm the founder and CEO of PG Analyze, but I'm also, a Postgres enthusiast, you could say. And so my goal here today is to basically tell you my sense of what I think is most noteworthy in Postgres 18. Some of the, key things that we're going to talk about is Asynchronous I/O, the new B-tree skip scan features, UUID version 7, and a bunch of other things. This is not, going to cover every little thing because there's just so many changes in this release. But, if you want to, try things out yourself today, you can literally just go and install things, try it out. And then, I would encourage you to share things with the community if you learn stuff about Postgres 18. That's what I always appreciate about Postgres is that, we can all get together and share our understanding of how Postgres works and how Postgres was improved. So let me hit the right button here. So we're going to talk about 7 things today. We're going to start talking about, actually, before I jump into the agenda, let me give you just a quick housekeeping note. So we are using the Q&A feature in Zoom for Q&A. So if you have any questions, feel free to throw them in the Q&A feature. And then I'll get to the questions at the end, unless there's anything that, really jumps out to me in the middle. And I should load this up here. Let me see. All right. So I got the Q&A on my side here. So if something really is pressing and I feel like I want to address it right away, I'll try to do that. But otherwise, we'll do that at the end. Our goal here today is that we're going to run for a little bit under an hour and then leave some time for Q&A at the end. And that's a good question. David just asked a question, will we be sharing this deck? Yes, we will be sharing those slides. You will, in fact, receive an email tomorrow morning, basically 24 hours after the webinar, which will have both the slides, the webinar recording. And if there's any questions that needed, follow-ups where where I didn't have the answer right away, we sometimes also include additional information in that follow-up email. But yes, the slides will be available basically tomorrow. Okay, I should take a glass of water. Okay, so we're going to talk about a bunch of things today. I'm going to start you off talking about asynchronous read I/O, which I think is one of the really key major improvements in this release of Postgres. Then we're going to talk a little bit about B-tree skip scan. We're going to move on to UUIDv7. I'm going to talk about a few highlights on the planner changes, how the Postgres planner basically has improved in this release. I'm going to talk about a bunch of explain changes, which are obviously related to planner, but basically, if you're optimizing queries in Postgres, there's a bunch of good stuff in this release that's going to make things easier. And then we're going to round things out by talking a little bit about plan ID tracking. I myself made a small contribution to this release, and we just released an extension called PG Step Plans, which builds on that improvement. And so I want to give you some context on where that might be useful. And then also, at the end, I included a list of other noteworthy changes where I didn't have the time or the context to really look at them in detail. Every year there's things that I just didn't have the time to look at, or that I just didn't think of even including. And so my goal today is that I give you accurate information, right? So if something is omitted, it might also be because I myself didn't have the time to research it in detail. And so my goal is that I try for things to be thorough and accurate, so that you actually know, it's not just stuff got faster, but actually why did it get faster? Or maybe in which cases might it have gotten slower, right? So my goal is to give you as much context as I have. And for context, where I learn these things, right, is I often like to read the Postgres hackers mailing list, which is where all the Postgres development discussions happen. And so, throughout the year, up until the feature freeze in April, that's really where you see a lot of these discussions on how these features get shaped. And so I try to stay on top of these things. And that's where a lot of my, background here comes in, basically, is in explaining these things to you. Let's start with asynchronous read I/O. So it's very important that we emphasize read here because this is really about making reads run asynchronously. And what do we mean with synchronous versus asynchronous? So this here is a diagram we included in the blog post we put out a couple of weeks ago, which I'll use a bunch of materials from that post, but I'll walk you through it in detail. So if you think about what is synchronous I/O versus asynchronous I/O, really it has to do with how a program schedules I/O or issues I/O, and then does it wait for that to return, right? So in the simplest case, in a typical Linux program, if you make want to read something from a file, you call a function, and that function does a syscall on the kernel. And then once the function returns, you got your data, right? And so what happens is if you have a program that's built that way, it will, make these piecemeal requests basically to well, here the kernel isn't shown, right? But like ultimately it goes to the disk if the data is not in cache. And so what you see here, right, is like the typical synchronous I/O where you basically make a read, wait for the result, then make the next read, wait for the result, right? Now with asynchronous I/O, what we're doing is we're basically changing that mechanism so we improve parallelism ultimately, and also we reduce the wait times, right? So the ultimate goal of asynchronous I/O is that we issue more I/O requests and we issue them together. In some cases, that also enables I/Os to be combined, right? So the operating system oftentimes can make a larger I/O request, which both for actual physical disks, but then especially for network storage in kind of our network environment in the cloud makes a big difference. And so with asynchronous I/O, which we'll see is basically a flurry of requests basically all starting, and then the program doesn't actually have to wait for each of these to return, right? Like it's basically able to issue the next one, the next one, the next one, and at some point it says, okay, now I issued a megabyte worth of I/O reads. Let me wait for the results now, and then continue kind of pushing ahead. So this is the core difference between synchronous and asynchronous. Now, important context here is Postgres 17 actually made a really important change here that basically, this has been a multi-year effort, right? Like folks like Thomas Freund, Andres Freund, Thomas Munro, many other folks have worked on this. And so Thomas actually committed a change into Postgres 17 that introduced an API for streaming data. So the read stream API basically is a new abstraction internally in Postgres, but what that enabled is for async I/O to hook into it, and so that when instead of Postgres program like pieces of Postgres having individual kind of activities that are doing, there's basically an API that says I want to read stuff from a table, read it as a stream, so that I don't actually have to wait for each result to return. And so in Postgres 18, what we have is this new method, this new setting called I/O method. And that basically controls how asynchronous I/O happens. So there's three modes that we can use, basically three methods that you can use. Sync is basically the same that existed in Postgres 17, right? So it uses all the same APIs, but instead of issuing things asynchronously, it actually does wait for the I/Os to complete. It does rely, like Postgres 17 did, it does rely on the OS prefetching to do some of the asynchronicity, right? So even in Postgres 17, I actually mentioned this commit message, I think, here at the bottom, where it talks about this POSIX F advice will need. So that's basically Postgres telling the kernel, I'll probably need those, 10 other blocks soon. And so the kernel actually had some asynchronicity in previous releases. And so if you use the sync method, right? Like you're basically relying on the kernel to do some of that asynchronicity, but really it's a much worse version of it. But if you're trying to, not change how stuff works or something, performed worse, then the sync method is something that's available. Now the new default is worker. And what worker means is that Postgres actually starts has processes running all the time that do I/O completions. So the idea is that Postgres basically, when you have a connection, and the connection, needs to read some data, it basically registers that interest in the backend. It, starts the I/O, but then it doesn't actually have to wait around for the I/O to complete. Instead, these I/O workers are the ones that are basically making sure that the state of the I/O operation, right, like whether it failed or whether, it succeeded, like what the data was returned, blah, blah, that all happens without, the main program needing to block on it. And so by default, you have a pool of 3 worker processes that are, if you started Postgres 18 right now, you would actually see these new I/O workers running and speeches that activity. And so what these workers do is they basically, they are the ones that have to ultimately complete the I/Os. So one of the things we'll get back to in a moment is you might have to increase them in some cases. If you have a lot of I/O activity, this may become, a bottleneck where you just need to raise this to 10 or 20 on big systems. Now, last, there's also a new method called I/O uring that builds on the Linux-specific I/O uring API. And this one basically is like from performance characteristics, is oftentimes going to be the fastest. It's only going to be available on Linux. But what IOU ring ultimately is, it's a way for a program to communicate more effectively with the Linux kernel to tell it which, IOs it wants basically, or which like kind of which file, which parts in that file it wants to read. And instead of doing a syscall, which, with all the kind of CPU like Spectre and what other kind of attacks, syscalls got more expensive, right? So to basically for security reasons. And so IOU ring actually is a lot more efficient because it minimizes that syscall overhead. It also avoids the need for having the workers. So if you enable IOU ring IO method, you don't have any workers running. One thing that's worth noting here is that you should use Linux 6.5 at least. The reason for that is that older Linux releases, especially if you have high max connections, the problem is that the high max connections plus an old Linux kernel basically makes IOU ring in the Postgres method not as efficient. And so I would recommend, like based on what I saw on mailing lists, basically use a new Linux kernel, and then IOU ring is a good choice. And it was a question regarding IOU ring on Red Hat 8. I'll research that for you and I'll send you the answer tomorrow because I recall the exact version and kernel versions being discussed. And I think Red Hat 8 might have been one of the kernels that's slightly too old, if I recall correctly. So benchmarking IO, AIO, is one thing we did, again, before the blog post, and I'm kind of just repeating the results here. They're still true. So what we did here is we basically went into AWS and we provisioned a large instance, like 32 vCPUs, bunch of RAM, with dedicated volume, with 20,000 provisioned IOPS, right? So this was basically a typical cloud setup for, dedicated Postgres database. It was a relatively small table, 305 gigabytes. And so we basically tested, how long does it take to just get the data from this table if you're just counting how many rows there are, right? Pretty simple test. And so on Postgres 17, that took 15 seconds. On Postgres 18 with the sync method, it also took 15 seconds. There's, slight variation in here, but I think it's basically within the margin of error. And then where it gets interesting is if we look at Postgres 18 with 3 workers, we get a significant reduction, right? So we're basically going from 15 seconds of runtime to 10 seconds of runtime with 3 workers. And then if we use IOU ring, it gets even better. We're going from, the 10 seconds to 5.7 seconds. So drastic improvement, right? Now, this is a very simple test. So obviously not everything is going to be bottlenecked on IO in the same way. But I just want to show you that, especially with cloud storage or also local storage, oftentimes the bottleneck historically has just been Postgres not issuing the IOs fast enough, right? And if async IO, that's really the big improvement here is that Postgres doesn't have these internal delays anymore. And so you're getting much closer to what the, either physical device or the network storage is actually capable of. So, big improvements here. If we look at this, in a kind of a comparison chart. So again, Postgres 17, Postgres 18 in the sync method behave basically the same. Blue here is the cold cache test. Red here is warm cache test. And so we're basically, seeing that didn't change. And then the cold cache performance, which is what I referenced earlier, that one, improved with workers. Adding more workers helped a little bit, right? So when we added 3 more workers, so it's 6 IO workers total, and it was just that one query running, right? That did improve, but then we didn't see any more improvements. But if you had concurrency on the system, of course, more workers might be necessary. And then IOU ring, again, performed the best. There's some interesting things here, which is why is IOU ring actually slower, right? Like if you think about this, like if you just look at the blue bars, it's a nice easy story. Like smaller is better, right? Like it gets better with supposedly the best method IOU ring. But then if we look at the red bars, right, like the warm cache line, we actually see that IOU ring is slightly slower than the worker method. And that is something to know about, right? Like as you're making that choice, like should you be using IOU ring? There is an edge case where if you have the data in the OS page cache, just the transfer from the OS page cache to the Postgres shared buffer cache is less efficient with IOU ring or less parallel with IOU ring. And so if you see a lot of, your workload not being loaded from disk, but from the OS page cache, then it may make sense actually to use the worker IO method. There's a bunch of other things you can tune in terms of settings in Postgres 18. So first of all, an existing setting, effective IO concurrency, that one used to be set to 1, which the community kind of realized it was a bad idea. Like it was doing just a tiny little bit of read ahead by default on the old releases. And so many people actually already tuned this to be higher, but now Postgres 18 basically makes a new default of 16, which means the idea behind effective IO concurrency is how many IO operations roughly should be in flight. And then really where the big difference is, right? Like with 18, that actually means how many IOs is Postgres issuing. And the way to understand this is if you basically look at effective IO concurrency, you also look at the new IO combine limit setting. Those two together basically define how much in bytes, how much Postgres actually reads ahead, right? So how many, if you multiply it out, I think 128 kilobytes times 16 gets you a couple of megabytes, right? So basically Postgres won't issue more than a couple of megabytes of worth of IO for a single backend because that, you're not gaining anything more after that, right? Like you might as well just issue the additional reads after you got some initial data back. And then if you're using the IO method worker, with the IO worker setting, you can actually control how many workers to spawn, right? Again, this is a worker pool that's always running. I would recommend raising this. So if you have a very large machine, consider, going up to 10 or 20 for that. And one thing you might ask yourself, right, is like, if I use the worker method, how do I know, if I need more workers, right? Like, is it the right setting or is it the wrong setting? And so one of the things you can look at, and I'm sure there's going to be more, best practices coming out as people, deploy this on large systems. But my understanding is that one of the things to look for, right? Like in older releases, you might have, if you look at wait events, right? So if you look at pgstat activity or you graph pgstat activity over time, you see that IO data file read event, which basically means Postgres is bottlenecked on IO, right? Like we see the wait event on IO. And so in Postgres 18, this actually changes because if you use the workers, because now the connections might wait on this AIO IO completion wait event. And then the data file read IOs are actually, or read events are actually on the IO workers. And so one of the ways you might, be able to determine, hey, do I need more workers? Is you see a lot of your connections, in the AIO IO completion wait event state, but you're not seeing the throughput you think your device has, right? So you basically know, like if you look at just your IO stats, you know that you bought more provisioned IOs or something, and you're not seeing the throughput you're expecting, then it may make sense to raise the IO workers. The other thing you can do is there's a new debug view called PGAIOs. And so PGAIOs actually just shows you the internal state of these IO operations in flight. And this is going to change really quickly, right? So this is not something that like I don't think there's a lot of value in capturing this in a monitoring tool like PGAnalyze because it's actually too short-lived, right? Like this is really, what's happening in this very moment. But if you're just trying to get a sense for the peak, like how many things are in flight, right? So don't actually look at the individual rows as much, but just try to understand in which state and how many of them. That could potentially help you, or if something is behaving odd, basically, right? Like if you're seeing something stuck for some reason. One of the things that was important to me, right? Because I work a lot with explain plans, and so one of the things I want to understand better, and I think I have reasonable understanding now, is when you enable I/O timing, you actually need to think a little bit more about what that means in Postgres 18. It's not that this really changed between 17 and 18; it's just a little bit more nuance to think about now. So if I look at an explain plan, right, like this one here, and this is what we ran earlier, just an explain analyze buffers and that. And so we see here that we have IO timings of 15 seconds, and we loaded 400,000 buffers in that time, basically, right? It's all shared reds. It all came from the OS page cache or the actual disk. Now in Postgres 18, right, my performance improved, and so it got better, right? And now I'm reading the same amount of data in less time. But what's worth noting is some of that happens because of the parallelism, right? So sometimes, basically, what people sometimes do, and I've also done this in the past, is look at IO time to understand how much effort the system had, right? Like how much work did the system do? And so if you're just looking at IO time, what you'll actually see is that, it goes down, right? Because Postgres spends less time in waiting, because that was the whole point of this, asynchronous I/O improvement, is that we're waiting less. But you might be surprised basically by just the fact that, you're still doing the same amount of work, right? So just because I/O time goes down doesn't mean that there's less I/Os being issued, because it's really the I/O wait time, not the time, not the time on disk or anything like that, right? So, worth noting about, and basically, in parallel query, for example, we actually get this reported back. Like if you have I/O workers, there's no mechanism that tells you 3 I/O workers waited on I/O for this long. Like it just happens behind the scenes. And so it's still good to look at this number, right? Like to understand if I/O time is extremely low, then you probably had the data in the OS page cache, but take it with a grain of salt, basically. And then last, to talk about async I/O, there's always the question of direct I/O, right? Because especially oftentimes, when there's like big press articles about what, Postgres does, and then, people are like, what, Postgres still doesn't use direct I/O, like it has all this double buffering problems. And so the good news is, right, like with 18, we made a really important step. Like we, as the people who worked in this, I didn't do any of that, but I've observed people do really important technical work for Postgres 18 to be able to eventually turn on direct I/O. And the big benefit of direct I/O, again, right, like it's that Postgres does not have that intermediate caching situation with the OS page cache. Like right now, you might have the same page twice in memory, right? Like you might have it once in the Postgres shared buffer cache and then once again in the kernel cache, which is really inefficient. And that's just a fact of how Postgres operates, and it has worked well for many years, but it's just wasteful in terms of resources. And so with direct I/O, we're just avoiding that OS page cache altogether. We're also able to get better visibility into just the caching situation. But worth noting, even though you could technically turn it on 18, right? So on 18, you could actually go ahead. Well, even on 17, you could go ahead and turn it on. It's just a different way of issuing the I/Os. On 18, if you only did reads and never did any writes, you could actually use direct I/O and it would perform reasonably. But the big problem is the write path doesn't have direct I/O, well, it doesn't have asynchronous I/O. And so because you don't have the operating system basically doing stuff for you anymore asynchronously with direct I/O, it's basically not usable yet on Postgres 18 because of the writes being too slow. So this is something that, folks are actively working on for Postgres 19. So my hope is that Postgres 19 will actually let us also enable direct I/O. But for now, with async I/O, you still have the double buffering. All right. And I'm going to come back to some of these questions towards the end, but thank you. Please keep them coming. So B-tree skip scan, totally different thing. Forget everything about async I/O. This is a complete different class of problem. So skip scan is something that again builds on something that happened in Postgres 17. So I always appreciate that there's many individuals in the Postgres community, and people oftentimes like take a long time to get improvements in, because it's tricky to change operating the database that has been around for so long, like longer than some operating systems. And so Peter Geoghegan has worked on B-tree improvements for many years now, and I always appreciate like his effort and his kind of grit in actually getting stuff done over the years, because this is hard, right? And so in Postgres 17, what he introduced was a improved handling of scalar array operator expressions, usually called in lists or any arrays, basically. Right, so you're passing multiple values to a scan, to an index scan. And so this mechanism that Peter introduced in 17 basically got a big improvement, or very different class of things it can do now with Postgres 18. So Postgres 18 introduces what's called here the skip scan optimization. When you see n-b-tree in commit messages, that just talks about b-tree. That's just how it's called internally. But the big improvement here is basically that we now have a better way of doing certain index searches. So this works best, in my understanding, this works best when you have omitted columns in your kind of where clause that are in the index but not in your query, and those columns have low cardinality. Right. So one example that we have here is, let's say we have 10,000 distinct A values and then 10 million distinct B values. Right. So we have create table A, B. We're inserting into that table but then, use the generate series function here, but we only have, like the 10 million divided by 1,000 means we only have 10,000 unique A's. Now we have an index that leads with A and then has B as secondary column, right? For B-tree indexes, the column order is very important. That still holds true. So if I did an index that was BA versus AB, the physical structure of the index looks very different. And then the query we're doing is we're doing select from that table where B is 100, right? So we're looking for a specific B value where we have those 10 million values, but we're not specifying any of the A values. And so if we look at this, Postgres 17, well, first of all, we get a sequential scan. So Postgres is like, that's a stupid idea, right? Like, why would you do that? Like, you're looking for something that's not the leading column in the index. Like, I'm just going to do a sequential scan. It's going to be faster, which is sometimes reasonable. One thing I also did here is I turned off parallel query. If you turn on parallel query, the sequential scan is actually faster. But if you have parallel query turned off and you also turn sequential scan off, which you'll see on 17, is that it basically, does the index scan, like it will do as it's told, basically, if needed. But it's pretty slow, right? Like it takes 130 milliseconds to do so. What it ultimately has to do is do a lot of index lookups until it finds, that particular piece. Now in Postgres 18, this is much improved. And in Postgres 18, in fact, I didn't have to change that setting, right? You can actually see this in the plan cost. So here in this plan, we see 35,000 as the plan cost. And if I go back to 17, you see there was 184,000 plan cost, right? So there was a reason, right? Like here, the sequential scan had less cost. So that's why it was chosen versus on, 18, and actually the cost estimate is lower. And so Postgres actually makes a different choice. And it makes a different choice for a reason, because now with the skip scan improvement, even though I'm not specifying the A that is first in the index, I can actually get this query to go from 136 milliseconds to be 22 milliseconds, right? So about a 5x improvement on the query performance, just because basically what Postgres does internally, right? Like it passes more information down to the actual index scan, and so as the index is being traversed, it knows what to ignore, basically, as it's walking through, so that more quickly it can find the rows that are matching to B100, right? So it's just a different implementation of that index scan. It's not actually a physical change in the index structure, right? Like the B-tree index itself is still structured the same way, but the search is basically done differently, because as that commit message talks about, there's basically these skip arrays that are built for the index scan, and then that basically contains the state where it's like, okay, let me skip over all the irrelevant values more quickly. So pretty cool improvement. You don't have to do anything to gain anything from this. The one thing worth noting is what we did here with creating an index, but then not actually using the leading column. This was basically an anti-pattern before, right? Like you really shouldn't have done that, because it's like if you're looking for B, just make an index on B, right? Like don't do a multi-column index if you don't need it. And so what's interesting about this change now is that we can actually reconsider some of that advice, right? Like it's still going to be more efficient to just have an index on B. But if we, sometimes you have complex workloads, you don't want to create too many indexes. And so now it actually is more viable to, have less indexes, but multi-column indexes, especially if those leading columns have less distinct values. Okay, let's see. So let's switch gears, and again, we'll come back to some of these questions towards the end. Let's switch gears to UUIDv7. So UUIDv7 is, might seem like a small thing, but it actually is really important, I think, in a real world workloads. And this one was unfortunately something that didn't get into 17, so I'm really excited that it got into 18. And part of that was just the finalization of the RFC, like the standard that introduced UUIDv7. It just missed the Postgres 17 release, but Postgres 18, there was plenty of time, luckily. As this was, a standard that was newly improved, right? Like this just hasn't existed historically. And really the key thing what a UUIDv7 does, right? UIDs are 128-bit like unique values, or that's the idea. But then what it introduces, instead of just being a random UID like UUIDv4 is, which is typically used, a UUIDv7 is a timestamp prefix UUID. And so timestamp prefix UUIDs, they have a 48-bit timestamp portion. They have a version variant portion in the middle, which all UIDs have, and then there's a random bit portion at the end. And so what this means is that if if you like, you can assign these, right? So it's not like you could have done this, like you couldn't have done this before. You could just had your application assign them. But now we can actually just call the UUIDv7 function in Postgres, which is built in, and it just will just give us a timestamp prefix UID without us having to do any extra work. And so, for example, now I can actually do a primary key column that has this as the default, right? So it's just much easier. And I would even go as far as saying you should probably never use a UUIDv4, especially if it's something that's indexed, right? So if you are indexing your UIDs, I mean, there's an argument for not using UIDs at all, but if you insist on using a UID, here's a very simple example, right? We create two tables. This is all on 18. We use the new UUIDv4 function for the old one, basically, right? So like currently in Postgres 17, you have gen random UUID, and that's basically now has an alias of UUIDv4. So UUIDv4 is basically the same as the old UUID generation function. And then on the first table, we do UUIDv7 for the IDs. Important thing here, we do first create the index and then we insert. If you did it the other way around, it would be a little bit different. But what we're simulating here is how an index bloats when you have random numbers, right? Because B-tree indexes are sorted and they really want sorted data. Like it's much, much better, much more efficient for a B-tree index to give it sorted data, like data that actually increments over time versus data that's just random. And so UUIDv4s are random. And so if we're creating an index and we're just throwing random data at it, we'll have to do a lot of inefficient kind of page splits and whatnot. And so just looking at this comparison, right, like the top one here is the UUIDv7, the bottom is the UUIDv4. We see that just in this simple test, a UUIDv4 takes about 80 megabytes more space, right? So UUIDv4 takes about 386 megabytes, UUIDv7 takes 300 megabytes, and those 80 megabytes difference, that's literally just index bloat that happened because of that random UUID. So really simple example, right? But this very much applies on any real life workloads. If you have UUIDs right now in your ID columns, you really should consider using UUIDv7 instead. Now here's some fun stuff with UUIDv7. So this is where, if basically be aware that this may not be a good idea, but you can extract timestamps. So you can actually know when this UUID was generated, right? Like that's the idea, is like it actually has a timestamp in the beginning. And so this was a UUID I generated this morning. And so it gives us the exact time when I generated that timestamp. And if you really want to get into funky stuff, basically, what you can do is you can do time-based partitioning on UUIDv7 values. So again, this may be a really bad idea, but I think it's just cool that this works, right? So here you can make a table and you partition, the table has an ID as a UUID, and you partition the table by range on the ID. And then your table partitions are the UUIDv7 values for particular timestamps, right? This is kind of abusing it a little bit. So if anybody contributed to the UUIDv7 spec and saw this, they'd probably be like, what are you doing? Why are you doing that? But theoretically, right, like what you can do is you can say there's a time-based partition that starts on, the 24th in the morning and ends on the 24th in the evening. And there's one for 25th and 26th. And so what happens is when I now, insert into this table with just the random UID I generated, then it will get placed in the right time-based partition, assuming it exists, because, again, there's a timestamp in the beginning and Postgres is just going to, say, well, this range partition is here, let me fit that value in, right? So that works. And then, of course, if you search for stuff, then it will just go across all the partitions. But if you know a specific UID, a specific ID you're looking for, it will just use partition pruning to find the right partition, right? So here in this case, when I look for that ID, just the fact that it's prefixed with that timestamp will actually let it prune down to the September 25th column table here. So it's just again, might be a really bad idea, but I just find it funny that this works. Last thing to note on a UUIDv7 is it can be a potential problem to adopt them everywhere where you use UUIDv4 right now. And the reason for that is because it is leaking a little bit of information, right? Because it tells you when something was created. And so if you don't want to expose that information in a like UID that you show to, a customer or in the browser or something, there have been efforts to try to, do something about this. I haven't used these firsthand. I just want to mention that in case anybody's interested in it. So UUIDv7 is basically something that takes a UUIDv7 and then uses a SIP hash to basically, or SIP hash, to transform that into UUDV4. And so on the client side, you basically get a UUDV4, but then it is able to also go back the other way, right? So there's basically a way to kind of encrypt the UUDV4 or like transform it in a way, hash it in a way that actually lets you show UUDV4s to the client that are random that you can't extract the timestamp out of, but then the server actually is able to take them again and turn them into UUDV7. So that may be of interest to somebody who is concerned about the timestamp aspect leaking. All right. Well, these were, the three major things that I really wanted to make sure you all know about. But there's many other things that, changed in Postgres 18. And so I want to give you some highlights of some of the planner changes. And then we'll talk a little bit about some explain improvements and then talk about plan IDs. And then we'll round it out with, the list of remaining things we don't have time to talk about today. So one of the things that's, just a neat improvement, and this is kind of, why would you do this in the first place is a good question, but let me try to explain to you the kind of situation here. So if you do a self join, and this is the example that was used in the original thread suggesting this. So if you make a table, in this case called TT, and there's an A and a B column, and you're doing selecting that table, but you're also getting the values you're searching for from the table itself again, right? So you're basically saying, give me all the B's that match that expression, and also just find them like find the rows again. And you might be like, well, would anybody do that? But turns out ORMs generate bad queries, right? So oftentimes it's not people writing bad queries. It's just that the ORM will do stuff because, a developer wrote the code in a certain way. And so the database, previously on Postgres 17 would have just gone ahead and did a join, right? Because, you're asking me to join two tables, I'll join two tables. Versus in Postgres 18, this specific example turns into just one scan basically without the join, right? So again, 17 that actually got all the data from the TT table first with a sequential scan, and then did point lookups again on the table to find all these values. Whereas in Postgres 18, it's able to realize that it actually is able to just collapse this down into one scan. So something that you can turn off if there is a reason you don't want to have this optimization. It is turned on by default. It's probably a reasonable thing to have on. But yeah. It's also worth noting that this was proposed in 17 previously, and then it got actually reverted in 17 like late in the cycle because of some issues. Those issues were fixed, and now 18 basically has it again as a more well-built feature. And then also another thing like very different is this is also one of the things where maybe your application generates something inefficient. So if you have a set of OR conditions. So here in this case, right, we have an application generating where ID equals 2, or ID equals 5, or ID equals 10. In Postgres 17, Postgres will just take this in and run a query with this. Don't pay too much attention on the difference between sequential scan and index scan here. They probably would use an index scan in both cases. But the key point here is that it gets passed as individual expressions. Actually, maybe, I guess I don't recall. Maybe it is actually index scan, sequential scan is significant here. But the point is, right, like if you think of, for example, that scalar array ops optimization, where Postgres is able to do more efficient B-tree scans, those rely on this, any array list, right? And so just having a list of OR expressions like this is much less efficient, performs much worse, especially if there's many of them, versus having an array that's being passed down is much more efficient. And so that now happens automatically. So if you're doing an OR in the same column again, Postgres will do that transformation for you. There is also a longer tail of other stuff that I just didn't have time to make slides for, but I'll give you some of the highlights here. So other things that changed in the planner in 18. So if you have like columns in a distinct clause, they do matter obviously, for what actual planner implementation or execution happens. And so previously, you could sometimes reorder columns to get more efficient query plans. Postgres is now smarter about doing that reordering for you, so you don't have to, move the keys around in a distinct clause. One thing that I'd love to have made slides for but didn't was write semi-joins. So just if you're interested in write semi-joins, look it up and please write a blog post about it. Incremental sorts. So if you do incremental sorts, just to explain what those are, is they're basically you have a result that's sorted, for example, from an index scan, and then you have another operation that needs that sorted result, but sorted a little bit differently. Like maybe there's another column that was added that also needs to be sorted. And so with this improvement in 18, merge joins now can also produce an incremental sort node and basically reduce the overhead, right? Because they don't have to resort the whole result. They can actually use incremental sorts. Partition-wise joins have been improved in various ways. This is something just worth noting that partition-wise joins are not turned on by default. So if you do a lot of complex stuff with partitions and you're joining them with other tables that also have partitions, look at the partition-wise join settings, and then you might find some useful improvements there also in 18. If you have your application generating in values clauses, that now is automatically transformed into an any, which is going to be more efficient. So just something that automatically happens, kind of saves you some optimization. And last but not least, there is actually some efficiency improvements in planning queries with many, many partitions. As people scale Postgres to even bigger systems, one of the things that people do is they create a lot of partitions for a given table. And so that will perform faster in 18. All right, let's talk about explain. So if you're using explain to optimize queries, you'll see a couple of things that look different there. So first of all, one of the things you might do is if you're optimizing a query, you might use the planner settings to turn off certain things, right? So you might say enable sequential scan off. In fact, I did this earlier in an example. And so previously in Postgres 17, the way that it was implemented internally is if those planner settings are turned off, the cost value is just extremely large, right? It's like 10 billion or something that gets added to the cost of a sequential scan. And that way it discourages the sequential scan. Now, the problem with that approach was that in certain cases, you might actually have extremely expensive operations. And so even though this was an extremely large number, there would have actually been reasons to make it even larger, basically. But then, that also seems like kind of a, we just got to keep making it bigger kind of problem. And so instead, in Postgres 18, there's a different mechanism that basically remembers which plan nodes are turned off. And so then it prefers anything that's not turned off, right? And so here in this case, now in the explain, we also see this differently. So you actually see the cost being the original cost, right? Like the sequential scanning here had this cost of 35, not the cost of, 10 billion 35. But it has this marker that is disabled, meaning if Postgres would have had any other choice, it would have taken it, right? Like if there would have been an index scan, it would have used it, but there just was nothing available. And so it did resort to that sequential scan, but it just tells you about the fact that this was disabled. So just worth noting, if you're looking at plans, you see that and you're wondering what does that mean? It's because you turned off a planner setting. Another key improvement, a key change that happened is that now if you do an explain analyze in Postgres 18, it will do the buffers option by default, which a lot of people are really excited about. I think it's a good change. Basically, if you don't have buffers, you don't know how much IO work something is doing, right? So on the left side here, we're doing a sequential scan, but we don't actually know how many, pages, how much data is being worked with. Whereas on the right side, we see that there was a sequential scan, that sequential scan hit for 45 8 kilobyte pages. So we have some sense of, how much work happened. This also helps, in a community context, for example, when people report performance issues to the performance mailing list, they're like, hey, my query is slow. And to give you an explain analyze output, now they will actually give you more information by default, which is going to be just helpful to really, identify the root cause of a problem earlier. The one thing I'll note on this, so first of all, interpreting buffers output does require some experience, right? So basically, do try to understand what these numbers mean. So there are 8 kilobyte pages is one thing on most Postgres installs. But also if you see the hit counter, right? So shared hit 45 here, be be aware that sometimes that hit counter can double count. So for example, if you do a nested loop join, the nested loop join will oftentimes access the same buffer page over and over again. And so that hit number might be extremely large, right? You might see something like 1 million hits, but the table is, only 10,000 buffer pages or something. And so when that happens, just remember that the hit counter does not count distinct pages. It just counts the page accesses, basically. So one thing to know about now that that pops up more often. The other thing to know about the buffers option is that it does have a little bit of overhead. So just if you see the times be different, I mean, even in this example, I guess we can see it's 2.5 milliseconds versus 2.7 milliseconds, might be margin of error. But if you see timing variations, it might be worth trying buffers off just to, confirm that the difference wasn't just the fact that buffers had to do more state keeping internally. This is, for what it's worth, something that I think is actually fixable, and I proposed a patch to Postgres 19 to reduce the overhead of buffers. So buffers right now has a bunch of unnecessary overhead because of how it's implemented. So maybe we'll see that reduced in 19. One nice quality of life improvement is that row counters are now shown as float values. So on the left side, right, we see a nested loop join, and we see, an index only scan, and it says, rows equals 0. And if you look at the explain output a lot, you might have seen this. You're like, 0 rows? That doesn't make sense. And so what happens, right, is like internally that was 0.5, but then Postgres rounded it, and so it became 0. And so in the example on the right, what you'll see in Postgres 18 now always is you'll see 2 digits of precision for any rows values. So it's just going to tell you more precisely, especially when the value is between 1 and 0, what the actual average row count was for each of those loops. Let's see. Okay, index searches. Yes, this is another thing. If you look at explain plans in 18, you might see this pop up and you're like, what's an index search? So this is also on by default if you do an explain analyze. And there's actually no setting to control this. It just shows on an index scan node. And so what it does, right? So here we see we do an explain analyze select from that table. We search for a particular ID, and then we have this list of 1, 2, 3, and then 10,000. That actually is significant because what I did here is I intentionally caused it to search at least 2 different things, because with the scalar array ops optimizations from 17, this would have just been 1 index search. So if you drop the 10,000, it becomes 1 index search. But if you keep the 10,000, it's 2 index searches because it basically descends the whole tree twice. And so lower is better, right? So if your index search is less, that means the index scan was more efficient. So generally, you want this number to be lower if you can, and you will also see that a lot of the improvements in 18 basically made that number smaller, right? Like that was one of the things that Peter Gagan, I think, used when he developed some of these B-tree improvements, is basically using the index searches metric as a way to understand, is the optimization working as expected? So just something to look out for when you're optimizing queries. All right, well, in the interest of time, let me move on to plan ID tracking and PG stat plans. And this is just going to be a quick version of this. I just want to give you something that, I personally contributed to in 18. So this was a patch that I co-authored with Sami Imse, and then Michael Poquier committed that one early this year. So what this does is it lets you set, it's titled Allow Plugins means extensions, to set 64-bit plan identifiers in plan statement. This seems very obscure maybe, so let me try to explain a little bit more. So in Postgres 18, you can now write an extension that sets a plan ID using a hook. And then you can use that to track statistics, right? So previously, like plan statements is basically, it's the output of the planner, right? So when the planner finishes its work, it produces this plan statement. And previously, that plan statement has a query ID associated. The query ID is what you might see in PG stat statements. But it doesn't have a plan ID associated. Plan ID is something that is new in 18. And so nothing in core sets this, right? Like query ID gets set by stat statements. Plan ID actually, or sorry, not correct. Query ID gets set by core Postgres. Stat statements uses it, but it's core Postgres setting it. A plan ID is not set by core Postgres, but extensions can set this to a certain value. And so what this lets us do is it lets us build extensions that track plan statistics. And so the idea is, right, like what I kind of wanted to build, I wanted to track things that track the plan shape of a query changing, right? So if I have like here, for example, the sequential scan on the users table versus an index scan on the users table, I want to know how often did Postgres choose a sequential scan versus a bitmap heap scan or a bitmap index scan here. And so this is an extension I built with a colleague of mine. This is released as of, well, as of PGConf Dev early this year, but it's now actually tagged as an official release. And so if you're interested in this and you have 18, please take a look at PG plans. This builds on this plan ID change to enable you to track plan statistics. It also builds on another 18 change, and this is, again, more for extension authors. But what you can do now with 18 is you can use Postgres's cumulative statistics system as an extension. So previously, the same thing that tracks things like pgstat user tables or, any of these internal kind of this object had this much activity, that same system now can be extended by extensions. And so it, first of all, saves you a lot of plumbing that you have to do otherwise, but it also lets you do certain things that you couldn't do outside of core. And so, what does this all mean? Like, how can I use this? With pgstat plans, I can actually just see, this query ID had this plan this many times, right? How often it happened. And then one of the things that really only works because of the AT change is that I can also get the plan for a currently running query. Again, this is not a Postgres 18 thing itself. This is if you combine Postgres 18 with this extension or an extension like it, you are now actually able to see query plans for a currently running query. And that works because the plan ID is set on that plan statement, right? Like an extension can now set the plan ID. And so you can use that as a way to tell another session what the plan ID that was used was. And so I think it's just a really, will probably take some time for the extension to be more widely available. But once the pgstat plans extension is available in all different environments, I hope that that's basically going to be something we can just have. So if I have a slow query and I'm like, what's this plan? I can actually just look at pgstat plans activity and get that plan for that query. All right, let's wrap it up. So just, some things that we didn't have time for. Obviously, it's hard to fit everything in an hour because there's so many amazing changes. So things we didn't talk about, I just want to tell you, that they exist and what they roughly are. So we didn't talk about OAuth authentication. If you're familiar with IAM authentication, right, like in the cloud, there's all kinds of things that providers have done previously. OAuth authentication is just a new way to actually have the OAuth protocol, so you don't have to pass a password. You actually have, the server speaking OAuth with the client. I think this is something where we'll actually see a lot more movement over, the next weeks and months as people test this and implement this. It's sometimes challenging in certain situations, like Google, for example. Google OAuth doesn't work directly right now. So, it's not something that I think is usable right now as an end user just yet, just because it requires a bunch of things to work together. But I think, eventually this will mean we have less passwords flying around. Second, virtual generated columns. So previously we had store generated columns, right? So the table could actually generate something and store it based on another value. Now this is, more of an ease of use thing. Now you can actually have something that is generated when you're querying the table. That is based on another column. And then another thing, I just want to point this out because some people are really excited about it, is temporal constraints. So now you can actually create constraints over ranges. Look this up in detail because I didn't look it up in detail, but it's been a multi-year effort as well as it goes for these Postgres changes. Some other things that are noteworthy improvements in my mind is if you have queries that access many relations, like many partitions, the locking performance is much improved. So this will just benefit you without having to make any changes. But kind of fast path locking basically just performs better and has more works more often for more tables. Vacuum changes, two vacuum changes. So normal vacuums can now freeze pages even if they're all visible, right? So regular vacuum usually doesn't, do anything with an all visible page, like we'll leave that to an anti-wraparound vacuum. But now with this change in Postgres 18, it's basically going to try to do a little bit of work ahead of time so that, the IO load is basically spread out over multiple vacuum cycles instead of just all happening in an anti-wraparound vacuum or an aggressive vacuum. Third, there's a new setting called auto vacuum max threshold. Vacuum max threshold. This really helps for certain tables where previously what you might have done is you might have changed the scale factor and threshold settings to set the scale factor to 0 and then use a fixed threshold. Whereas what this does is by default, I think 100,000. If you have 100,000 dead tuples, it will automatically kick off an auto vacuum, even if it's a very large table, right? So it basically will reduce the need to fine tune vacuum settings because you will just get more reasonable behavior on very large tables where only a small portion is being updated. So just a really good practical improvement. And then there's some work going on around NUMA and kind of, like understanding better how different, NUMA nodes and the CPU architecture kind of affect Postgres. And it's just worth noting that there's a bunch of views that could add to PG buffer cache, more for debugging purposes, I would say, but interesting nonetheless. And I realized this list should say 3 more things to know, so that's a mistake. But there's 3 more things to know, which is checksums are now enabled by default. So if you do an initdb on like a new database cluster, you will now get checksums on by default. Checksums just mean that, if there is a like faulty page, you actually know about it versus the server silently corrupting. So it's a good change, but it does add a little bit of overhead, right? So if you're seeing a newly initialized cluster perform worse than a newly initialized Postgres 17 cluster, just be aware that checksums are one of the differences between the releases. Doesn't change on upgrades, right? So if you have an existing cluster, you're upgrading it, it's not going to turn on checksums like you actually have to, I think, dump and restore, if I recall correctly. So more for new releases. MD5 authentication is now officially deprecated, so people should really use Scram SH256. MD5 is no longer, considered to be good. Is officially deprecated, so really try to see if you can update your clients to support it if you haven't. And last, and this is the reason I put this so late, is because it's actually not something I think in my understanding, you can't benefit just yet on this, right? So PG17 to PG18 can't benefit from it, but PG18 to PG19 will benefit from the fact that planner statistics can be preserved during upgrades. So if you are, excited about the next release and you want to upgrade to it, it's going to be much less impactful because the planner statistics, like the analyze run afterwards, doesn't actually have to happen. It has reasonable statistics from the get-go, basically. All right. Well, that is all. We have a bunch of questions. Probably going to do, maybe 5, 10 more minutes of questions. We'll also send out the recording, right? So if anybody has to drop, feel free to drop, and we'll send you the recording and the slides tomorrow. And thank you, everybody, of course, for joining. Let me look at some of these questions. And I think I'll probably go by time. So I'll start with a question that Nikhil asked in the beginning, which is around, I think IO. Whoops. Nope, that was not what I wanted. Let me fix the screen share. Okay, let's see, kind of go back. There we go. Okay, so Nikhil asked a question, which is, can all selectors use this setting? And I think he was referencing probably the settings in the very beginning. So let me jump back there. Okay. So I imagine it was probably related to these settings. And Nikhil, if that's not true, feel free to ask another question and I'll do it with answer async. But basically, I think the question was, is this going to be used by all select queries? Are there any limitations? And so, yeah, the good news is basically this does get used pretty much throughout the board for, I think, at least sequential scans, bitmap, heap scans, but not yet for index scans, I believe. That's my understanding. So I think index scans do not yet use this infrastructure, but bitmap heap scans will use the infrastructure. And so, but in any case, it's better than what was there before. So like really the big improvement, right? Like it's like there's really no reason why you need to change any of these settings. A lot of these settings are like IO concurrency and IO combine limit, I think are per connection settings. IO workers actually do require at least to reload. I think there's another max IO worker setting which requires a restart. But yeah, like some of these settings like an IO method is also something that requires a restart. So I think there was another question that Emil asked, which is I think related, which is it possible to get the best of both worlds by using a combination of IO U-ring and workers, right? So if we, I guess, let's look back here, right? So we had this one case where IO U-ring was actually slower than workers. Like, could I switch this on a per connection basis or per query basis? And the answer is no, right? So this is actually something that you have to choose. Let's see, yeah. So the choice of the IO method, right? Whether you use worker IO U-ring or sync is something that requires a restart. And so because it has to, initialize stuff differently internally. And so, yeah, I would say, the default is good. Like use worker, worker works well. No, nobody has reported anything really off of worker, right? And so IOU ring, if you enable it, just do benchmarking beforehand. Try to understand if the problem is really that you might have this one situation where you rely on the OS page cache a lot. But yeah, unfortunately, you can't mix it. Um, all right, then Rohit asked a question: should we use direct IO on read replicas, which are read-only workloads? See, that's an interesting question. I haven't really thought about that. Right. So, like Rohit asked this question in the context of what we had here, which is, could I use direct IO? And I think it's worth benchmarking. I haven't done it. I am aware of, some like Andres Freund, who, authored a bunch of the Async IO work, I think has stated publicly in some places that it might be reasonable to use direct IO on 18 in certain cases. Maybe that's one of these cases. He hasn't said that, but maybe he hasn't, thought of it explicitly. So I would suggest give it a try. Um, Again, it's write operations that are a problem, right? So I know, for example, wall writes are an issue with 18 and direct IO, which is why it's not, usable for a primary. But maybe you're right. Maybe a replica doesn't have that problem. And I think you should be able to change the IO method on a replica because, you can use different settings. So worth a try. All right. Let's see. Nikhil asked a question. Does B-tree skip scan apply for multi-column indexes only? That is an excellent question. Um, I think it is. And in fact, if we look at the commit message, we see that right here. So, Peter's commit message here says teach MB-tree multi-column index scans to opportunistically skip over irrelevant sections, right? So the which kind of makes sense, I guess, right? Because like the whole point here is that it's skipping parts of the index that are not relevant to the scan. And the part that's not relevant is basically a different column that's indexed, but not in the right, like not in the query. And so I think, yeah, if you just had a single column index on A, you couldn't use that for the search on B. If you just had an index on B, that would work just fine, right? Like you wouldn't need the skip scan. So yeah, skip scan is only relevant for multi-column indexes. All right. And then I think Johannes just made a note, but I'll share it in case anybody's interested. So I think this was in the context of UUIDv7 and v4. So I think Johannes just noted that basically the one of the reasons why you might use v4. So at the very end, right, oops, we talked about, let me see. I guess here, right? So we have UUD v4.7, and so I think Johannes mentioned that v4 could be helpful if you intentionally don't want your data to be ordered, right? So the v4 basically let's see, where do we have it here? Yeah, so we have the v7 method and the v4 method. So v4 method will give us a random value, and so if we're searching, maybe if we're returning data and we don't want the data to be ordered, then v4 can actually be a good thing, right? So I think really my recommendation to use v7 was specifically for if it's indexed, right? Like it really like where it makes a big difference to use v7 is if you create an index on that column, then you really should use v7 instead of v4. And then I think Saish had a similar question or related question, which was, are the results the same on this particular test here if we insert the data first and then we create the index? In the interest of time, I won't run it, but definitely feel free to run it. What I would expect to happen is I would expect it to be much closer, if not the same, right? So what we see here with this difference between the two indexes with 300 megabytes versus 380 megabytes, that really happens because you're doing individual like inserts, and then the index kind of, it doesn't know the data ahead of time. Versus if you do an index built on its own, like if you flip the order here, I think it sorts the data as part of the index build. And so it would know where to put the index data in the first place. So you shouldn't see that discrepancy. Really, what this test shows, though, is if you have inserts happening, right, like over time, that's really where UIDv4 performs badly because the index structure deteriorates, basically. Like you get a lot of empty pages over time. And then Arul asked a question on how can we migrate from UIDv4 to UIDv7? That's a good question. That's tricky because right, like it's in a physical data structure. So if we want to, ch change a physical table to have all V7s, we actually need to change our data. And so that might not be viable for an existing application. Like it might just be something that, I mean, you could do a new ID field or something, right, and just assign all new IDs, but it's probably not worth it. You could theoretically mix it, right? Because it really is about the values you're generating. So you could, change the default and just understand that you have a mix of V4 and V7. Um, that might be a way of doing it. All right, and then let's keep going. I have a few more questions, and looks like we definitely have more questions than we can get to. So I'll do 5 more minutes of questions, and then we'll do the rest async. Um, so let's see. So Ivan asked a question about are there edge cases where Postgres would not use collapsed optimized self joins? So Ivan has a case where there's many, many complex self joins. Um, to answer your question, yes, there definitely are edge cases where this would not use self joins. In fact, as I was putting together these slides, I made an example and it didn't work as expected. So the answer is yes, it won't consider all the cases. I would suggest if you're interested in the specific mechanisms, it's probably worth just going back to the mailing list threads. So if you search for well, if you look at the commit message, like every commit message in Postgres has a note to the discussion. And then if you look through the discussion on the self-join elimination thread, there was a lot of discussion, I think, well, on the technical implementation, but also on what it actually does. And so I would probably start there and I would just take a look at, what like when it works and when it doesn't work. I'm not an expert at this myself yet, so I'm just sharing what I've learned so far. But I would start that mailing list thread and try to understand, you know, what mechanisms it uses to identify it. All right. Let's see. So Lauro asked a question. Do you have any information about the weighted partition pruning improvement, which actually allows pruning to happen with similar data types and with subqueries? The release notes say it's fixed, but I tested partition pruning and it's shown no difference in the execution plan. Weighted partition pruning. I know there were changes in partition pruning. Let me look into this, and I'll see if I can include a note in a follow-up email tomorrow. Because I don't know it right off the bat. I'm familiar with some of the partition pruning changes, but I don't know. I know something. I want to say something was revised maybe, but it could also be that your particular test case, is different. Like it's hard to say, but I'll see if I can dig something out, and then if not, what I would recommend doing is just send an email to the mailing list, right? Like the Postgres mailing lists are really the best place to actually reach the people who built the features. And so there are people who work in partition pruning. So if you just send an email to either PGSQL General or PGSQL Performance, those are the two mailing lists that I think are appropriate to ask that question on and be like, here is my query. I expected this to get better in 18. It didn't, is this expected? And then that should get you a good answer as well. But I'll see if I can dig something out for you. And then let's do 2 more minutes and then we'll do the rest async. So Chris has a question. Is there a risk in changing the default value from generating UUIDv4 to UUIDv7? It won't change the existing data. And yeah, that's correct. So yeah, like you can basically, if you want to go in and you just change your table definition, right? Works, I'll go back, right? Like if you wanted to just do alter table test two in this case, and set the default to UUIDv7, you totally could, right? Like that, there's no reason not to do it. You just have a mix of UUIDv7s and v4s in your table. But for example, the indexes would actually improve in their performance for any new data being inserted, right? Because the new data would be sorted at least. So you could certainly make that change, I think. And then let me do 2 more questions. Okay, so Letitia asked a question. Why the 10,000 makes it search twice? I think that was a question related to skip scan. Oh no, it was a question related to explain. Well, skip scan and explain. Let's see. So here. Okay, so the question was, why are there two index searches here? Right? Like why if you remember what I said earlier, is if the in list here is in 1, 2, 3 versus if the in list is 1, 2, 3 10,000. Why did the 10,000 cause it? Well, it's not on the slide, right? But basically, when I put the slide together, I did a test and it was showing index searches 1 if there was the 3 values in the beginning, and if I add the 10,000, it's 2 index searches. And so that has to do with how the actual implementation, like this again, is more like the precursor for the skip scan, right? Like it's that scalar array op implementation in 17, really, where if you're searching for 3 values that are on the same index pages or they're very close together, like it's basically adjacent index pages, then Postgres as of 17 can already eliminate a lot of traversal of the tree, right? Because it's actually passing down, like on 16, for example, it was doing 4 index searches for this case, right? Like it was doing index search for 1, index search for 2, and index search for 3, and index search for 10,000. Now, as of Postgres 17, and this still holds true in 18, it's doing 2 index searches here. One index search that's able to search and find in one tree traversal 1, 2, and 3. And then because 10,000 is so far away, right? Like physically in the index, that value is just in a very different spot. And so that index search can't find it. It actually has to retraverse the tree, look at, go through different kind of intermediary nodes basically to get the 10,000. So that really explains the difference here, right? It's because the physical distance between those values. I will actually, in interest of time, I don't want to, make anybody stay unnecessarily longer if they want to just wait until the end. Also, I sometimes find it helpful to do research, so I'll stop here. What I'll do is anybody who asks a question, you'll get an answer, or I'll tell you at least what I know. But we'll do this async, so I'll this all goes in the spreadsheet, and then you'll get an answer tomorrow as part of the slides or in the email. We'll include some answers and some research for you to know more about Postgres 18. So yeah, thank you again for joining. Really appreciate everyone making the time, and I'm looking forward to this release. Hopefully, it will be a good release, and you'll all have faster production systems. Thank you everybody for joining today.